Okay, so in this next segment, we'll be pushing forward with the concept of covalent bonds and talking about how we can use Lewis structures to help understand what sorts of covalent covalently bonded molecules form. So the main learning objectives, let's switch over to the tablet, are going to be in this segment. Drawing electron dot diagrams for atoms and simple molecules, showing how ionic and covalent bonds are represented in Lewis structures, and stating the octet rule and showing how correct Lewis structures obey this rule. Okay, so in a covalent bond formation, one of the major driving forces is to simulate a noble gas electron configuration whenever possible in a new compound or molecule. So what we mean by simulate here is that we are going to be completely filling the s in all the 3p valence orbitals with unshared or shared electrons. So in a Lewis structure, we say that we want each atom to be surrounded by a noble gas configuration of 8 electrons. And so it doesn't matter whether they're shared or unshared. So for example, here the chlorine, it has these 3 lone pairs of electrons. And it also is sharing these 2 electrons with phosphorus, and that obeys the octet rule. It essentially has filled s and p orbitals. They're not really s and p orbitals. They're orbitals that form from combining the orbitals of the phosphorus and the chlorine. But you have these new orbitals, and they are filled with electrons, either unshared electrons or shared electrons. Now, the other 3 chlorines are the same. The phosphorus, on the other hand, has 6 electrons that it's sharing, 2 in each bond, and then 2 more here for a total of 8 electrons surrounding it. So what we see is that essentially in Schrodinger's equation, so these Lewis structures are essentially just summaries of complicated results, both observed, seeing which molecules are stable in experiment and also looking at Schrodinger's equation, that solutions to Schrodinger equation in which each molecule has 8 electrons in its orbitals, either shared or unshared, those are particularly stable. So we would predict that since this molecule obeys the octet rule, it should be a fairly stable molecule. Of course, except for hydrogen, the goal is to get noble gas configurations. And hydrogen, it can only get up to helium. You'd have to add way too many electrons to get up to neon. So hydrogen fills the doublet rule because it's trying to get to the helium structure. For example, here we've got one hydrogen sharing, both 2 hydrogens sharing the same electron pair. You have H2, and H2 is a relatively stable molecule because because as it shares those 2 electrons, then the entire molecule is stabilized because each is approaching a noble gas configuration. All right. Okay, so the first thing we do in electron structures is for any atom, we start with the atoms and we draw dots for the valence electrons. Remember, we talked about the importance of valence electrons here. The electrons that are not valence electrons are really not available for covalent bonding. So lithium has 1 valence electron, beryllium has 2, boron has 3, carbon has 4, nitrogen 5, oxygen 6, fluorine 7, and neon, noble gas, 8. It already has a noble gas configuration. It doesn't need anything to be in a noble gas configuration, so it's less likely to actually share electrons with other things. And the same thing goes for elements further down. Remember, covalent bonds are generally non-metals interacting, so that's what we'll be focusing on. Yes, so great. So Lewis structures for ionic solids are pretty simple. We've got lithium. Here's the Lewis dot structure for lithium and the Lewis dot structure for fluorine. So all we do is just move that ion over, and so lithium would be the Lewis dot structure of lithium is just that, lithium with no valence electrons and a positive charge, and fluorine with 8 valence electrons and a negative charge because it has 1 more electron than it would be to be electrical neutral. And that's it. That's the Lewis dot structure for lithium fluoride. Pretty simple. But Lewis dot structures are really designed for covalent bonding. So say in this case, we have oxygen reacting with 2 hydrogens. So we're going to write it such the two dots are there, the two dots are there. And if we have two dots that are shared, we replace those by lines. So now oxygen now has 8 valence electrons around it, 4 that are in lone pairs and 4 that are in bonds, and hydrogen has 2 electrons around it, satisfying the doublet rule, that are both in bonds. And so what we suggest is that H2O should look a lot like this: 2 lone pairs and 2 hydrogens. Now, exactly what the shape is, we'll see, what comes from that, later lectures. But that would be the Lewis dot structure for H2O. Double bonds and triple bonds. So for oxygen, in order, if you have O2, which we know is a nicely stable molecule, it'll need to share 2 electrons in order for both of the atoms to share a full octet. And so if there's 2 electron pairs being shared, 4 electrons being shared total, we'd write that as a double bond. Nitrogen has 5 valence electrons, so in order for N2 to form, it would need to share 3 electrons. And so we write it, instead of like this, we write it with 3 lines in between to represent this nitrogen triple bond. So we would predict that nitrogen would triple bond, that would have a very strong bond because it's sharing 6 electrons in that. And N2 actually is a very, very strong bond. And O2 is a fairly strong bond, stronger than, for example, the bond in H2. Okay, so let's just pause and think a little bit. We're going to do a lot more with rules of Lewis structures next time. But let's just look at the Lewis structure of H2O, H3O, and H3O plus. So if we have the Lewis structure of H2O, we already saw that. We have H dot, O, 1, 2, 3, 4, 5, 6. We get sharing here, and everybody can happily have a full octet of electrons. Great. But what if we say, well, why not H3O? What about H3O? We've got we start with H2O. And so if we add another hydrogen, that is going to be bringing in it's going to be bringing in another electron. So we'd have H, but there'd be 1 more electron there. You have, the oxygen now has 1, 2, 3, 4, 5, 6, 9 electrons around it. And that extra electron is going to be pushed into some higher energy level. It's not particularly stable. So H3O, we predict, is not very stable. I mean, you could get it, but it would immediately react and fall apart. So how about H3O plus, though? So H3O plus, we already know this is the hydronium ion, so we suspect it might be relatively stable. We've got how many valence electrons? So we've got 6 from oxygen, plus 3 from the 3 hydrogens, minus 1. We're taking 1 electron away. So what we would get is, instead of having the 3 electrons there, there's just 2 electrons there, and there's an overall positive charge. That's how we would denote the overall positive charge of the hydronium ion. And this does satisfy the octet rule. Now oxygen has, the hydrogens still have 2 electrons around it, and the oxygen has 6 bonds shared in single bonds, and then 2 more lone pairs for a total of 8 electrons around it. So we'd predict that unlike H3O, H3O plus is actually going to be relatively stable. And it is, and we see it quite a lot in acids. There's lots of H3O plus floating around. Okay, so that's the basic idea of Lewis structures, what the octet rule is, and how we start with the Lewis structures of atoms. Next time, we're going to be digging a lot more into how do we draw Lewis structures of complicated atoms and predict exactly what's going on, complicated molecules. Atoms are not that complicated. You saw what they are and what the Lewis structures are. Predict the Lewis structures of more complicated molecules and show how powerful it is in really understanding exactly what's going on in these covalently bonded molecules.